All right, welcome YouTubers to statics. This is actually day one of statics, the very beginning, addition and resolution of forces. And so let's start off with the definition of what these things actually even are. So the first thing that we need to talk about is a force. And when we use the word force from this point forward, what are we referring to? We're going to define a force as something that's acting on a body with some kind of magnitude and direction. And hopefully you recall, if something has magnitude and direction, it has to be a vector. Okay, and our second item that we need to define is a resultant force. And if we're looking at a resultant force, basically it's the result of adding other forces together, or you end up with some kind of single force, and that single force must be equivalent to whatever the other forces you're adding together. So in our most simplest form, if I were to look at some kind of box sitting on the ground, and let's say I'm going to apply a couple forces to this. Let's say that I'm pushing this box forward with a force of 6 newtons, and I have some kind of force holding it back. Probably frictional force would be the most common, of 4 newtons. Doesn't get much simpler than this. And I want to define the resultant force. Give you a second to do it in your head. You can break out your calculator if you need it. If so, I feel a little bad for you, to be honest with you, because really what we're just saying is if I wanted a single force to replace those 2 forces, I have 6 going forward minus 4 going back, leaving me with a resultant force of 2 newtons pushing forward. Now, that was nice and easy because it was all linear. Of course, things get much more complicated when they aren't as linear, so let's talk about some additional ways that we can add these vectors together. Addition of vectors. So let's say that the first method I'm going to talk about is called a graphical, or the parallelogram method. And with this method, the way this works is if I had 2 vectors, let's say I have some kind of vector A and I want to add it to some vector B. What I'm in essence doing are drawing 2 lines that are parallel to the other 2 vectors. So I draw a line that's parallel to vector A, I draw a line that's parallel to vector B, and where those 2 intersect would be where my resultant force, now my resultant force starts where the other 2 started, we're at the tails of both those vectors, and ends up at that intersection point. So the magnitude of this resultant is just equal to vector A plus vector B. Now this can actually be drawn to scale and measured, which you hardly ever see. Definitely not required for any class that I teach. So most people don't walk around with rulers. Instead, what we want to do is mathematically determine this, and one way we can use this is by using the triangle rule. If I were to look at this parallelogram method, and just from my previous example, let's say they have the same vector A and the same vector B, instead of just drawing a line parallel, what I can notice is I can just move A. If I were to move A down to the tail, or to the head of B, so the tail of A is now at the head of B, and were to connect those 2 lines, then I would end up with my resultant R. In the same manner, I could have also moved my B, the tail of B, to the head of A. So this would be my B, vector B. So I can see it's just like the parallelogram method, but instead what I'm doing is just moving these vectors around head to tail. So that's the key to this method, is that the little 3 dots, if you haven't seen that, little bowling ball looking thing, means that therefore we can add our vectors head to tail, and this works with multiple vectors or in any order. So if I look at what I just did, I would have vector A plus vector B, whatever that looks like, gives me this vector R. Certainly this does not look like my other example I was just drawing, but that's okay. And I can also start instead with vector B, add vector A, and I end up with what should be the same magnitude, same direction vector R. So what that basically means is they can be added in any order. If you remember what that is called, or if you don't remember what that is called, it is called commutative. Yeah, actually. So in essence, what that means is vector A plus vector B is the same as B plus A. Little vector review on day one. Static starts off so easily. This actually works with as many vectors as you may want to add together. So I'll say works with 3 plus vectors, and as long as you're adding them from head to tail. So if I have some vector A, who knows what that might be, I'm going to add some vector B, who knows what that might be, and I might add some vector C over here. However many I add, when I come to the resultant, I'm going to start where I started, adding all of these together for my tail of the resultant, and my head is going to be wherever I ended up after I've added all these other vectors from head to tail. Of course, mathematically that becomes much more difficult, so we'll look at some alternative ways to do that in the not too distant future. It also helps. Now let's go ahead and look at a couple little trigonometry functions that you'll need to know in order to solve these problems. So as a short little trig review, brush up on that trig. Most people forget these. If I have my standard triangle, and what I'm labeling are each one of my sides is a lowercase a, b, and c, and my angles opposite the a would be a capital A, opposite the b is a capital B, and opposite the c is a capital C. So I can tell the difference between sides and angles in between. I have two different laws that I need to be familiar with. I need to remember. One is the law of sines, arguably the easier one, which says the length of any side divided by the sine of the angle across from that side is equal to the length of another side times the sine of the angle opposite that side, which is equal to the third side. The other one, a little more difficult but not too bad, is the law of cosines. So law of cosines basically states that a squared is equal to b squared plus c squared, so that looks like a little Pythagorean, but because this isn't necessarily a right triangle, we have minus 2 times the magnitude of b times the magnitude of c times the cosine of a, which is in between b and c. So of course you can rearrange that. If this is, depending on what you're looking for, I could just as easily say that b squared is equal to a squared plus c squared minus 2ac cosine whatever I started with, right? So you can rearrange that and make that work. Hopefully remember that. All right, let's take a look at one quick example. And this example is going to involve a stake being driven into the ground. Here's my fancy dancy little stake. I'm going to draw my ground. I'll draw it in blue because I don't know why. Probably should use like a brown or something, right? Very cool little hatch marks in here. It'd be so much easier if I just used some kind of textbook image, but I didn't. With this stake in the ground, we're going to pull with two different forces. One force we're going to call P, some generic P, and the other force we're going to pull with 120 newtons. And as far as the angle for these two vectors, the P is going to be 30 degrees from the vertical, and the 120 newton force will be 25 degrees from the vertical. So what's given is this stake. And what we would like to find in this case is what kind of force P would I have to apply in order to get a vertical resultant. So with that in mind, I know I'm going to add these vectors from head to tail. So what I have is I have the 120. This is the way I did it anyways. Remember, you can add them in any order, but in this case what I chose to do was say that I had 120 Newton force in one direction, and I'm adding P to that. And when I add this P, the key is that this vector P needs to end up with a resultant. I'll draw a resultant in a different color so we can identify the resultant. It has to be vertical, straight up and down. Here's my resultant R. The hardest part to these problems is coming up with the angles. In this case, you have to use a little bit of trigonometric knowledge. So this P, I know if I drew a line vertical, then this angle has to be 30 degrees. And basically just looking right there and saying from the vertical, it needs to be 30. And then I know the 120 from the vertical. I know that this R has to be vertical. So that's my 25 degrees. And if that's 25 degrees, then I know interior over here also has to be 25 degrees. I'm sure that's a trig function that I can't remember, alternate interior angles type of thing. And then I also know it's 180 degrees along this vertical line, so I can take that 180, subtract out 30, subtract out 25, and I'm left with 125 degrees for that angle. I know that the sum of three angles of a triangle has to be equal to 180, so 180 minus 125 minus 25 leaves me with 30 degrees. So I went kind of quick through that because I assume that should be a review. And now it's a matter of saying if I want to figure out what this P is equal to, or the R, in this case it's only asking for P, is that right? I could find either one though. What do I need to do? Which law do I want to use? Law of sines or law of cosines? And what I do is I always like the law of sines more, so if I can find anything where I know a side and I know the opposite angle, then I can use the law of sines, which is the case here. So using the law of sines, what I can say is the magnitude of one side, which is 120 newtons, over the sine of the opposite angle to that, which is 30 degrees, must be equal to whatever I'm looking for. In this case, I said I'm looking for what P is needed, what force P over the sine of the angle opposite to that, which is 25 degrees. Punch that into your fancy dancy calculator, and I get a total load of 101.4 newtons. So that's a brief introduction into this addition and resolution of forces, and I will look forward to talking to you soon. Thanks.